plan for today is to, I'm not quite sure whether I've got enough time to do what I'd really like to do today, which is to go right through the whole of the Shor's factoring algorithm, but skimping a little bit on details. So when I show you something that can fairly obviously be done in not too many steps on a quantum computer, I won't stop and really carefully demonstrate that, and there'll be other little details like that. I want to give the big picture of the proof. And the advantage of doing things this way, which I have the freedom to do this kind of thing because it's a graduate course, I think, is that then I can go through the proof twice. I mean, then maybe in the next lecture I'll sort of remind you what all the steps were. Because it's actually there are a number of different steps, and I think it's probably a proof where it's quite easy to get lost and suddenly forget why, so many sort of, it's enough to be able to do this, and then it's enough to be able to do this, but now we can do this and we can do this, that you suddenly sort of lose your feeling that you're connected with getting a quantum computer to factorize a large integer. Anyway, so I'm going to try, as I say, to give the proof, but not absolutely every last detail, and then in the next lecture I will discuss some of the details a little bit more. My estimate is that the course is going to finish. When I started, it had indeterminate length. It was a maximum of 12 lectures. I think actually it's going to be 10, so I think it's going to finish at the end of this week. We'll see. These estimates have a way of being underestimated. Right, so last time I made the simple observation that if you've got a large integer n to factorize, if you can find a non-trivial square root, then the fact that that's a non-trivial square root of 1, the fact that that's a square root of 1 means that you can say that that's congruent to 0, in other words, n divides plus 1, x minus 1. If it's a non-trivial square root of 1, then neither x minus 1 nor x plus 1 is itself a multiple of n. So n has a non-trivial common factor of at least 1 of x plus 1 and x minus 1. And once you find a factor, you can then iterate the process. So if you can always find the factor, then you can iterate the process. Or if it was product of two large primes, then finding a factor was what we were trying to do. It was entirely what we were trying to do. And then I also made the observation that if you want to find a non-trivial square root of x, then a way that could in theory work is to find some y and work out what the order of y is. So we find a minimal r such that y to the r is congruent to 1. Because if you can do that, and if you're lucky enough for r to be even, then you just take y to the r over 2. And if in addition you're lucky enough that y to the r over 2 is not minus 1, then you've got a non-trivial square root. Now one of the details that I'm not going to talk about in this lecture is that if you randomly pick a y, then you'll be lucky enough for this to happen with probability at least, I'm not sure what it is, a half or something probably. Maybe, yeah, I think a half will do the job. Yes, because actually I can more or less sketch proof. At least if n equals pq, this is not really a proper proof, but there are 4 types of square roots according to whether you're plus or minus 1 mod p and plus or minus 1 mod q. So basically it depends whether y is a quadratic residue mod p or a quadratic residue mod q, and by the Chinese remainder theorem, each possibility will have a probability a quarter, and there are 2 of the 4 possibilities that you're interested in, so probability a half, and if you've got more factors it's just going to get even better. So that actually hides a useful piece of randomized algorithm philosophy, which is you don't have to get things to work for sure. You just have to make sure that their failure probability is not enormous. So if something works with probability 10%, do it 100 times, and then at least one of those times it will work with extremely high probability. Sorry, quantifiers. With extremely high probability, at least one of those times it will work. Okay, so we've reduced the problem to the following question. I give you a capital N, I give you some integer between 1 and n minus 1. What is the order of that element in the multiplicative group mod n? What is the smallest power that gives you 1. Now, of course, I made this remark last time, there might not be such a power because the number you chose might not be co-prime to n. But if that happens, you just apply Euclid's algorithm and get yourself a factor of n. So we're not worried about that. And if n is a product of two very large primes, then the chances that you accidentally hit on a number that's got a common factor with n are pretty small. So n has 100 digits, and you might have 10 to the minus 50 chance of that, or a P and Q have 50 digits each. So the problem we've got then is we pick a y. What is the order of y? I think I'm going to switch from y to x. If we can solve the order finding problem, then we can solve the factorizing problem. So now let's concentrate on the order finding problem. But before I go into how to solve the order finding problem, I want to go back now to remember we had here's our target, which is factorizing, and here's our starting point, which is the model of quantum computation, and we're trying to get from there to there. And I did a little bit of explanation of quantum computation, and I've done a little bit of reduction of the problem of factorizing, so now it's got to order finding. Now I want to go back to the quantum computation side of things and just see what sort of things can we do with a quantum computer, and these things will meet in the middle. It seems that I could obviously go in either direction, but at this stage I think if I were to take another step back from order finding, it would be introducing all sorts of slightly unmotivated things. But I will just say, what we're going to be trying to do is reduce the order finding problem to a problem that we can solve if we have a very fast means of calculating Fourier transforms. So what I'm going to do now is tell you what the discrete Fourier transform is, and explain why the discrete Fourier transform is something that can be done very fast on a quantum computer. And I know there are some people here who have discrete Fourier transforms coming out of their ears, so they should just take a little nap for half an hour or so, occasionally raising a little eyelid to check what my normalization is, which will be slightly different from the one they're used to. Okay, because the reason for that is, I'll say now, if we're doing quantum computation, we want the Fourier transform to be a unitary map. So we want to divide by root n. That's it. Now you really can go to sleep. So supposing I've got a function. Function from the group of integers mod n to the complex numbers. Let me just write down a formula for discrete Fourier transform. And it goes like this: f at r equals, and here's my normalizing factor to make it unitary. I'll prove that it's unitary in a moment. Sum over all x, and that's the sum over all x in Zn. Fx to the minus 2 pi I Rx over n. And as with other Fourier transforms, the choices that I had when doing this were what factor to put here and whether to take a plus or minus here. The factor here, the traditional factors might be 1 over root n or 1 over n. Normally these days I favour 1 over n for reasons I won't bother you with. But as I say, in the quantum computation world, we want it to be unitary, and 1 over root n is what you need. Why don't I just check that straight away? So, there are two ways of thinking about it. One is to say, what we're really doing is expanding f in a different basis, in the basis of trigonometric functions. And any two trigonometric functions are orthogonal to each other, and if you put the 1 over root n, they become not just orthogonal but also normal, therefore it's a unitary map. But let me just, I'm going to do it in a slightly more babyish way of simply working out what the L2 norm of f hat is. So, proof. this is the sum of squares of f. So what do we get? We get 1 over n, sum over all r, and then this thing squared. Sum r, and I'll expand out the modulus squared, which is again some sort of thing. If you do discrete Fourier transform, this kind of argument becomes very, very automatic. So I've got the expression for x and then the expression with x replaced by y and everything conjugated, and trick of wide applicability is when you haven't quite decided what to do, and while you're thinking about it, you change the order of summation. So let's do that. And let's bring the r as far to the right as we possibly can. For the benefit of hindsight, I'll bring the 1 over n as far to the right as I can as well. E to minus 2 pi r x minus y over n. And this thing here is delta xy. If x doesn't equal y, then you're summing over a whole bunch of roots of unity that are equally spaced around 0. Or if you prefer, just sum the GP. You get the first term minus the term after the last divided by the common difference. And the first term equals the term after the last one. That argument seems to work even when x is equal y, but then you can't divide by 1 minus the common difference. The common ratio, there's then a common ratio of 1, so you just have to add them all up and you get 1n times divided by n. So this easily works out to be delta xy, so therefore this is sum x fx squared, which is exactly what we wanted it to be. Just a direct verification. And the other thing which you can check in exactly the same sort of way is the inversion formula. I'm going to do a number of little calculations like this. So fx is more or less given by the same process in terms of its Fourier transform. Sum r f hat r. The only difference is that I replace the minus by plus equal to 2 pi r rx over n. And let's just quickly check that one as well, should be faster than I was last time. Proof. Well, let's put RHS instead of that. The right-hand side equals 1 over n, so I've got a normalizing 1 over root n there, and then I'll take another one from the definition of f hat r. So sum r, and f hat r was, I'd better put a y instead of an x, sum y, fy, e to the minus 2 pi I ry over n, e to the 2 pi I Rx over n, which looks really, it's not quite, but at the moment I thought maybe we had up there, but it's not quite, but it's jolly close. Again, I won't do this. We bring the r across again, and then we get equals sum y fy delta xy because of x for more or less the same reason. Now, we're going to use the Fourier transform in a really quite elementary way. Let's just make the following observation. Suppose I took the function f of x equals e to the 2 pi I, let's call it something like ux over n. If I apply the Fourier transform to that, then f hat of x, or f hat of r, so if then f hat of r is going to be 1 over, oh, actually, sorry, I want f to have norm 1, so let's put 1 over root n. Then f hat of r is 1 over n sum r e. So I'll put in the f of x, which is e to 2 pi I ux over n, and then I have to multiply by e to the minus 2 pi I rx over n, which equals, I think that's going to be delta ru. So that should be sum over x, of course. So when I sum over x, then if u minus r equals 0, then I'm summing 1 n times and divided by n, so I get 1. And if u doesn't equal r, then I'm summing over some nicely spread around roots of unity, getting 0. So if I draw a graph, I started with a function f that kind of looked trigonometric, and then when I took the Fourier transform, I ended up with a delta function, and the place where it was 1 is, so that's saying that f hat of r is 1 at u and 0 everywhere else. So it's picking out this u here, it's picking out the phase of this trigonometric function. So you can use Fourier transforms to pick out phases. Now that's true when the phase is a multiple of 1 over n. What we're going to do now is see what happens if the phase isn't quite a multiple of 1 over n, and things get just a little bit less pleasant, but not quite so unpleasant that they can't be used for Shor's algorithm. So Shor's algorithm, at some point we're going to find ourselves, we're going to manage to build a function of the form e to the 2 pi I alpha x, so for f of x equals, or maybe divided by root n, and we're going to say if we knew what alpha was, we'd really be in business and we'd have found the order of some number mod n. So I'm going to show you how, now, if you've got a means of calculating Fourier transforms, then you can estimate quite accurately what alpha is. So when alpha is not a multiple of 1, if alpha was a multiple of 1 over n, this tells us that the Fourier transform will tell you exactly. Imagine this was a quantum system. We worked out the Fourier transform. We got the following superposition of states, namely 1 for this state and 0 for all other states. Then when you do the measurement, you get precisely what this state is. When we do things, that's just looking ahead a little bit. You don't have to think in quantum terms. But what we're going to do is show that when alpha is not actually 1, we get something more like this. We'll wiggle and it goes up and then sort of wiggles a bit and decays pretty fast. And we will be choosing our capital N to be large enough so that the approximation we get for alpha is good enough for our purposes. But all that will come a bit later on. It's just giving you some motivation for the following calculations. I'll leave that picture there to inspire us. So actually, that's no longer really, strictly speaking, a well-defined function of Zn, because this depends on which, doesn't just depend on the residue class of x. So by this I mean x is a number between 0 and n minus 1, the purists. Whereas before, when I wrote this sort of thing down, I could choose any representative of the residue class and it made no difference. Actually, it's slightly semi-important point. But let's work out this Fourier transform. So we get f hat of r equals 1 over n, sum over all x, of e to 2 pi I alpha minus r over n x. And I'm going to use that to get an upper bound for the modulus of f hat r. So that implies, well, let's do that next. So let's just see what this is. Because we can calculate this as it's a sum of the GP. So it's 1 over n times the first term, which, since I'm going from, perhaps I better just write x equals 0 to n minus 1, just to emphasize what I'm doing here. So it's 1 over n. So the first term is a 1. The term after the last one is e to 2 pi I. So I'm taking x equals n alpha n minus r over 1 minus e to 2 pi I alpha minus r over n. 1 minus common ratio. So that implies the modulus of f hat of r is less than or equal to 1 over n. Now the top has modulus at most 2. This is a very standard sort of calculation. Anyone who's looked at Weil's inequality will have this sort of thing, will have done this kind of calculation. And let's just think about how we're trying to get an upper bound. So what's the smallest that this bottom part could be? Well, let's just draw a picture. Suppose alpha minus r over n, or 2 pi I alpha minus r over n is, or 2 pi alpha minus r over n, so let's call it beta. Suppose I've got an angle beta. How small can this distance be? Well, I know that the arc length is beta. Unfortunately, this can be smaller than beta, but it's clear that the ratio of the arc length to the actual length is minimized over here. And over here, we get that the arc length is pi, and the actual length is 2. So pi over 2, let's say that if we've got the arc length, then the worst that we have to do is multiply by 2 over pi. So that tells us, if you believe that argument at all, that this is at least the figure 2 pi times modulus of alpha minus r over n, and I've got to make it smaller by a factor of 2 over pi. So, whoops, what have I done? Just go back to what I had before. Smaller by a factor of. That's better than I thought, actually. So that worries me. I think it is okay though. So the worst that can happen is that I multiply by 2 over pi, which is the ratio of 2 to pi. So I get 4. And it couldn't be less important than this, because all I'm going to care about in the end is that it's true up to a constant. But I think we've got a slightly better constant than I had about an hour ago, which is always an odd feeling. So what we're actually going to be interested in is going to correspond to taking a measurement and asking what's the probability when we take a measurement that we are not close to our target alpha. So it will be interested in an expression of the following form. So that implies that the sum over all R such that alpha minus, say, R minus alpha n modulus is greater than or equal to k r squared with a 1 over n, sorry, without the 1 over n, is less than or equal to I prefer to make it useful, actually it's easy to think about that, but just stick with alpha minus r over n and put greater than or equal to k over n there. Well, the worst that can happen is that you've got one thing that's within k over n, and another one that's within k plus 1 over n, another one k plus 2 over n, and then something the same on the other side, something within k over n, something within k plus 1 over n. So we get 1 over n squared times 4, that's the 2 over 4 squared, and 1 over alpha minus r over n squared becomes n squared over k squared. And now I want to sum over all, I'll put j squared, sum over all j greater than or equal to k, and double it. Let me just say what I've done there. I said the very, very worst thing that could happen is that you find some r that's within k of n alpha and another one that's within k plus 1 of n alpha and so on, and the same thing in the other direction. And you just calculate what this is in all those cases. So I'm summing over all j greater than or equal to k on one side and summing over all j greater than or equal to k on the other side. And this is the expression we get, which is sum, so half sum j greater than or equal to k 1 over j squared, which is less than or equal to, let's be really, that, which equals 1 over 2 j minus 1, k minus 1. So I think I can safely say less than or equal to 1 over k for the k that we'll actually choose. So anyway, the main point is it goes down like 1 over k. In fact, even more the main point is that it tends to 0, as k tends to 0. And perhaps even more than that, I can just say if I choose k to be 10, then the chances that when I do a certain measurement, I won't be within 10 over n of the alpha I'm looking for will turn out to be at worst 10% or something. So what we've established is that, let me draw a picture, we've established that the Fourier transform of this function, fx up there, its L2 norm is sort of concentrated in a little interval of constant width, mod n. So the way we're going to estimate alpha is just to do a measurement which with high probability will give us something in this interval, and that will be therefore a very good approximation to alpha. But what I haven't told you at all is where this alpha is going to emerge from. And I also haven't told you at all how to do Fourier transforms on a quantum computer. So let's do the Fourier transform first of all. Before I do it, I want to make a remark for people who know about, which I imagine quite a few people, Fourier transforms on arbitrary abelian groups. So the Fourier transform on an arbitrary abelian group is what you get when you take the basis of characters, which is an orthonormal basis, and expand in terms of that basis, roughly speaking. This is an example of that. The characters are the functions of the form e to 2 pi I rx over n. and we're expanding in terms of those. But if you look at the group Z2 to the n, which somehow feels like the natural group to be looking at when you've got a cube 0, 1 to the n, the characters there are functions of the form -1 to the r dot x. What do I mean by that? So r is some binary sequence, x is another binary sequence. In a product is just sigma ri xi, and then you take -1 to that. So that function would be function corresponding to the character that's given by binary sequence r. Now, I'm not expecting people who haven't seen this at all to take that in instantly. I just want to say, to make the remark, that working out this Fourier transform with a quantum computer is extremely easy. And this is connected with why Hadamard gates are called Hadamard gates. So if you remember, a Hadamard gate was the one that took, well, it had a matrix 1 over root 2, 1, 1, 1, minus 1. And if you apply a Hadamard gate, so that just applies to one bit, so it takes the state 0, a little reminder of what quantum computation does. It would take 0 would go to the superposition 1 over root 2, 0 plus 1, and it would take 1 to the superposition 1 over root 2, 0, minus 1. And then if you take a Hadamard gate and do it to each bit, you get, well, you're going to get the tensor product of all these 2 by 2 matrices, which gives you a 2 to the n by 2 to the n matrix. And if you sit and do a few calculations, you find that the matrix can be defined inductively as follows. So you start with a 1 by 1 matrix, a 2 to 0 matrix, a 0 matrix. From that you produce the next matrix, which is 1, 1, 1, minus 1. I'll forget the 1 over root 2. Each time I do it, I'm going to multiply by 1 over root 2. At the next stage, I take 4 copies of this. Except the last one, I make minus what it was before. And in general, at the k stage, I've got AK. Then at the k plus first stage, I've got that matrix. And it's easy to check that the rows of these matrices are all, well, the symmetry in the rows are orthogonal. And with the 1 over root 2, they become unitary matrices. This is a 4 by 4 Walsh matrix. And a Walsh matrix is a specific example of a Hadamard matrix. And a Hadamard matrix is any matrix with plus or minus 1s that's orthogonal. And the little open problem is, do there exist Hadamard matrices n by n whenever n is a multiple of 4? And nobody knows. However, when n is a power of 2, or when n is a power of 2 times some n for which you've already produced a Hadamard matrix, then this construction gives it more often. And the Walsh matrix here is precisely the matrix of the Fourier transform associated with the group Z2 to the n. So Fourier transforms in the group Z2 to the n are completely easy with quantum computation. You just apply a Hadamard gate to each of the bits separately, and bingo, you've got a Fourier transform. And this was something that had been spotted before Shor came along, but Shor, I haven't actually looked into the history of the whole thing very much, but what I've picked up, I think, and this is sort of not guaranteed to be correct, is that quite a lot of, if you could do this, then you could factorize n, all that sort of thing was known before Shor, and it had been observed that Fourier transforms in Z2 to the n could be done very simply, not surprisingly as it is really very simple. Shor's achievement is to observe also that the Fourier transform in the group Z2 to the n, which is just a cyclic group mod 2 to the n, could also be done surprisingly simply. Even that is not absolutely a bolt from the blue, because there is something called fast Fourier transform, which makes use of clever is a sort of clever way of making use of the fact that you have a group of size 2 to the n. But I don't know. It may feel a little bit strange when I show you how simple it is to work out the Fourier transform even model in the end. I'm going to write down a formula for it and just check that it works. And it looks quite easy. And I sort of feel that Shor's achievement, everything ends up looking quite easy once you've really come to grips with it and once you've taken into account what was known before you did it. And yet somehow, just sort of daring to think that you could solve a really serious big problem using quantum computation and dealing with the various little technicalities that arose along the way. And sort of just doing it at a time when people weren't at all familiar with, and people hadn't been reading on the internet 150 treatments of Shor's algorithm before he went to devise his algorithms. I think it is a pretty remarkable achievement, despite the actually mathematical simplicity of it. Here's a formula. Now this is one of the places where I'm not going to give full details today. I'm just going to write down the formula. And I think it would be highly plausible that what I write down is something that a quantum computer could do very, very fast, just because it's simple enough. So a little bit of notation. Take a sequence of north 1. So we'll identify x with the number that it corresponds to in binary representation. So if it'll be sum k equals 1 to n, xi 2 to the, sorry, xk 2 to the n minus k. So x1 I'm thinking of as the most important bit, so it really is the number x1, x2, x3 up to xn. And then if I write something like that, that's the state. And I'll sometimes think of that as the state corresponding to the integer x, and sometimes to the binary sequence x. This is a place where the Dirac notation is quite nice, because you can just you can sort of write things like 3, and that's the sort of normal 1, 1. But we can also think of it as 3 over A. You know, if we wanted Schrödinger's cat, we could have 1 over root 2 z alive, and that sort of thing. Just quite fancy. All right, so the Fourier, what I claim is that the following formula is precisely the Fourier transform in the group z2 to the n. I'm just going to tell you what happens to a single computational basis state x, and then we'll extend it linearly. So by the way, the state x in the old language would correspond to the function that's 1 at x and 0 everywhere else. So the formula is x maps to 0 plus e to the 2 pi I, or minus 2 pi I, point xn. Point xn, I should have mentioned this, is just a binary. I'm so tempted to say binary decimal, but I can't really say that. So 0 point, there's a point A1 just so I can really have stated it, it's A1 over 2 plus AK over 3 to the K. It's just notation for that. Point xn minus 1 xn. Not forgetting the normalizing factor, 1 over square root of capital N, let's say once and for all, capital N equals 2 to the little n.
Should there be a 1 after the e to the n?
Yes, thank you very much. In both cases, of course, yes. All the way down to 0 plus e to the minus 2 pi I point x1 xn. Now, if that's true, then what's that saying? Well, it's saying to work out the Fourier transform, I'll first of all look at the first bit, and I'll multiply the phase of 1 using, in a way that will depend on just the last bit of xn rather simply. And then I'll turn attention to the second bit, and I use the last 2 bits of x in order to determine how much to multiply the phase of 1 by. Multiplying a phase by some constant like this will certainly be a unitary map. It will have a matrix to form 1, 0, 0, e to whatever it is. So roughly the number of steps is going to be 1 for this, and then 2 for this, and so on up to n for this. It's going to take me roughly little n squared steps. I hope that's pretty believable. And I'll try and be a bit more convincing about that next time. I see that I'm not going to get nearly as far as I thought in this lecture. But let's just see why this slightly odd looking, just simply can't put these ones in. Let's see why this should give us the discrete Fourier transform. So to do that, I want to look at the coefficient of the state R on the right-hand side. So to check this, which, by the way, we can also think of as R1 up to Rn as a binary sequence. This is just a little exercise. Of course, what I've said, I wondered about whether I should give some account about where this comes from, writing this down. Then I thought, well, I think it's sufficiently believable that you could get something like that just by knowing what you had to do and thinking, I want to do things bit by bit, and there are ways of doing that with the fast Fourier transform, etc., and just sort of working it out. And when you see how the verification goes, I think it makes it even more plausible that just by going away into a dark corner for long enough, Peter Shor could have got this one to work. So how do we pick out the coefficient of the binary sequence R up to Rn? Well, we just pick a naught from the bracket every time it's... what is this? Just remember what this meant last time. It just meant that attached to some state like that, you just took the coefficients that you got from each bracket and put them together, and it's just nothing to it. And this thing is identified with the sequence. That's just a different notation for the same thing. So all we're going to do is pick out either a 1 or an e to the minus 2 pi I times some stuff, according to whether Ri is norm or 1. So we get times the product it's a j, very technical but I, and you realise you shouldn't, so j equals 1 to n, and I want to pick out a 1, which I won't bother to mention, every time Ri is 0. So actually what I want to say is not j equals 1 to n, but the product of all j such that I equals 1 of e to the minus 2 pi I point x, and in the jth bracket I start at n minus j plus 1 and go all the way to xn. Now there's a small observation, which is that if I add an integer to this bit here, it makes no difference. So that's 1 over root n. Oops, product over all rj equals 1 e to the minus 2 pi I. So this number is just x divided by, there are j things here, so it's 2 to the j. And I can't tell you how many times I wrote things like 2 to the n minus j, and I got stuff later on. So this one's okay. Products outside exponentials are quite nice things, because they tell us to sum inside exponentials. So let's do that. E to the minus 2 pi I, take an x outside, sum rj equals 1 over 2 to the j. That number is especially similar to 0.r1 up to rn. So this is 1 over root n e to the minus 2 pi I x times r. There's a capital N, because capital N was 2 to the n, which is exactly what we want to do. Because if you now look at, so what would a general function be like? It would be something like sigma fxx. Remember, this is the name that we're giving to the delta function of x. So this is a way of thinking of the function f. So what is, if we apply this funny map to it, we'll get this, but we'll be summing over f of x. So we'll get 1 over root n, sum over all x, f of x, e to the minus 2 pi I x r over n. And that's exactly the formula that we had for f hat of r. So what I've shown there is that if we chose some function and applied this map, then the coefficient of the state r would be f hat of r. So I started with a function where the coefficient of the state x was f of x. So in fact, basically what I've done is I've shown that that maps under this funny map to sigma f hat r. R, which is exactly saying that this thing here is calculating the discrete Fourier transform. And I said it took about n squared steps, but that's for working out a Fourier transform on z 2 to the n, which is a much, much bigger root than n squared. So it really is incredibly fast. I haven't got time to do very much else. So next time I'm going to, but I certainly won't do the next thing, because one really rather clever idea that comes next. So let me just reiterate something I said last time about why it is the case that this unbelievably super fast Fourier transform is not something that people, that you can just sort of exploit to do all kinds of wonderful simulation on computers. It's because where is this Fourier transform living when you do it? It's sort of living in some incredible superposition of states. The one thing you certainly can't do if you've got a big superposition of states is say precisely what all the amplitudes are at every single point. How would you do it? Once you say you just decided to measure the amplitude at one point, you wouldn't even measure the amplitude actually, you'd just get the modulus squared of its amplitude. And you'd only get that by measuring it over and over and over and over again until the probability that you get that particular thing sort of stabilizes, and that'll take you really rather a long time. So what you have to do is just, you can use the fact that you've got Fourier transforms, but you just have to, whenever you do that, at some stage you've got to collect everything back up again into something that you can measure by just making it come back into a delta function. If you've got something that's too spread out, it's not too much use. I suppose it would be enough if you could somehow concentrate it in the left half of the cube or the right half of the cube and then measure which half you're in and extract some information like that. But you don't just get it from what the, so to speak, the wave function is. Anyhow, next time you'll see, we'll take a very simple state. We'll think of it as a superposition of some other states. We'll do some stuff to those other states, corresponding to finding orders of elements of the group, and then we'll sort of, that'll use a Fourier transform. That will give us, I beg your pardon, some functions that look like e to 2 pi I alpha x, and then we'll do some inverse Fourier transform to get a handle on what alpha is. And, well, I think I have to say that next time. Yeah. So I think actually I thought I was going to get to the end of this week, but only by dint of adding in a little bit of extra material. But actually I think I may be able to get right to the end of this week, just talking about Shor's algorithm. So I'll finish the sort of general view of the algorithm. So next time I'll be able to say, oh, we know how to do Fourier transform. And then I can go back to giving an overview of the whole argument. And then we can, I think the remainder, sort of, how would you actually devise a quantum circuit to do this? What precisely are the simple unitary maps, which, when composed, give you this map, that sort of detail. I'll do some of that, and maybe I'll do the whole lot, maybe I won't. Probably people won't mind if I don't do absolutely everything. But probably will mind if I don't do anything at all. I'm totally hand-waving. So I think I will just aim to finish by the end of Friday. Where I've got to, that's where I've got to. We'll definitely have the overview by the end of next lecture.